Hello everyone, welcome to Physics online classes for class 12 students. Let us continue chapter 6 Electromagnetic Induction. Today we are going to study about mutual induction. In the previous class, we studied what is self-induction, what is self-inductance and its SI unit, and also we derived self-inductance of a solenoid, and then we derived energy stored in the coil equation. Now let us study about mutual induction. So first we have to know what is mutual induction. Mutual induction is the phenomenon of production of EMF in one coil due to variation of current in the other coil is called mutual induction. That means if current is changing in one coil, one more current is produced in another coil. That is mutual induction. But in self-induction, what happens? In the same coil, current changes. In the same coil, again, one more current is induced. But here, we are going to consider two coils. Is it clear? It is the phenomenon of production of EMF in one coil due to variation of current in the other coil. So now let us study in detail about mutual induction. You can observe this circuit diagram. We are going to consider a pair of coils P and S. There is a pair of coil here. First one is primary coil, which is denoted by P, and the second one is a secondary coil, which is denoted by S. We considered pair of coils, primary coil and secondary coil. Now, this primary coil is connected to battery and plug key. This primary coil is connected to battery as well as tap key, or you can take it as plug key. Then secondary coil is connected to galvanometer. So these two coils are placed side by side without touching each other. These two coils are very close to each other parallelly, but they are not touching each other. Is it clear? We consider two coils, primary coil and secondary coil. Primary coil is connected to battery and tap key. Secondary coil is connected to galvanometer. We know that galvanometer shows the presence of current. Then we are going to induce EMF in the secondary coil using primary coil. That means the production of EMF takes place in the secondary coil due to variation of current in the primary coil. If in the primary coil current changes, then induced current takes place in the secondary coil. Yes, observe here. The first point, when current in the primary coil is increased using this tap key, when this tap key is pressed, current in this coil increases from 0 to maximum. When current increases, the magnetic flux linked with both the coils also increases. Observe here, when the tap key is pressed, current in the primary coil increases. This current is surrounded by magnetic field. So the magnetic field is linked with both the coils because secondary coil is kept very close to primary coil. That's why magnetic field linked with both the coils also increases when tap key is pressed. When magnetic field linked with coils increases, due to increase in this magnetic flux, induced EMF takes place and hence current is produced in the secondary coil. Where the current is produced? In the secondary coil. Why the current is produced in the secondary coil? Because magnetic flux linked with both the coil is increasing. Why flux is increasing? Because current in the primary coil is increasing. Why current increases? Because we are pressing the tap key. So, when current in primary coil changes or increases, induced EMF or the current is induced in the secondary coil. Similarly, the second point, the induced current in the secondary coil generates magnetic flux. Observe here, whatever the current is induced in the secondary coil, so this current also generates magnetic flux. This magnetic flux induces EMF in the primary coil. Observe here, when induced EMF takes place in the secondary coil, current is generated in the secondary coil. So the current in the secondary coil is also surrounded by one more magnetic flux. That magnetic flux is also in contact with the primary coil. So when that magnetic flux changes, then induced EMF takes place and hence current is produced in the primary coil. When current changes in primary, induced current takes place in secondary. Again, when magnetic flux linked with the primary because of secondary changes, again the current is produced in primary. This is mutual induction. When current changes in one coil, induced EMF takes place in the another coil. Is it clear? So the induced current in the secondary coil generates magnetic flux. This magnetic flux induces EMF and hence current is produced in the primary coil. When the current is produced in the primary coil, this current opposes the growth of battery current in the primary coil. Observe here, we already studied self-induction as well as Lenz's law. Whatever the induced current takes place, this induced current always opposes growth or decay of the battery current. Is it clear? So it opposes growth of battery current in the primary coil. And this is indicated that deflection in the galvanometer. Observe here, once again I will explain. We considered two coils. Primary coil is connected to battery and a tap key. When the tap key is pressed, current in the primary coil increases, so that magnetic flux linked with both the coil increases, induced EMF takes place, current is produced in the secondary coil. Here the current is produced. Now, this current is surrounded by one more magnetic flux. That magnetic flux, when it changes, again the current is induced in the primary coil. Whatever the induced EMF takes place in the primary coil, this induced current opposes growth of the battery current. Similarly, when I am going to release the tap key, current in the primary coil decreases, magnetic flux linked with the both coil decreases, so that induced EMF takes place in the secondary coil, hence current is produced in the secondary coil. This current is again surrounded by one more magnetic flux. When that magnetic flux decreases, again induced EMF takes place, hence current is produced in the primary coil, and this induced current in the primary coil opposes decay of the battery current. Anyhow, this induced EMF always opposes growth or decay of battery current, or in simple way we can say that induced EMF opposes change in the battery current, that may be increasing or decreasing. So we are going to call it as mutual induction. Yes, what is mutual induction? The phenomenon of production of EMF in one coil due to variation of current in the another coil is called mutual induction. Right. Now we can learn about coefficient of mutual induction, or we can call it as mutual inductance denoted by the letter capital M. We already studied about self-inductance. The same procedure here we can follow. Let we considered pi is the magnetic flux. What is pi here? Magnetic flux. This magnetic flux is linked with the secondary coil due to flow of current in the primary coil. Magnetic flux linked with the secondary coil due to flow of current in the primary coil. So I am going to write the equation pi is directly proportional to I. What it mean? Magnetic flux linked with one coil due to current in another coil, or magnetic flux linked with secondary coil due to variation of current in the another coil. Both are directly proportional. So we can write magnetic flux is directly proportional to electric current I. Or we can write pi is equal to, instead of proportionality sign, we can write a proportionality constant, and that is M into MI. Let us take it as equation number 1. What is M here? Where M is proportionality constant. What is M here? M is proportionality constant and this is called mutual inductance. What is M here? M is mutual inductance, or we can call it as coefficient of mutual induction. Pi equal to Mi. Let us take it as equation number 1. Now let us differentiate equation number 1. Differentiate equation 1. We will get d pi divided by dt is equal to M is proportionality constant. We cannot differentiate, keep as it is. Remaining is di divided by dt. So we know according to Faraday's law, E equal to d pi by dt. So in place of d pi by dt, directly I can write E equal to M di divided by dt. So this equation we can use for mutual inductance, or we can write it as M equal to E divided by di divided by dt. So this is the equation for mutual inductance or coefficient of mutual induction. Is it clear? Suppose if di divided by dt, change in the current with respect to time, if it is equal to 1 ampere per second, then the equation becomes M equal to E. Mutual inductance is equal to induced EMF. That means mutual inductance between a pair of coil is the EMF induced in a coil due to unit rate of change of current in the neighboring coil or in the another coil. What is mutual inductance? Observe the definition here. The magnitude of induced EMF in one coil due to change in the current through the other coil. When current changes in the other coil, induced EMF takes place in the first coil. This is called mutual inductance and the equation is given by E equal to M into di by dt or M equal to E divided by di by dt. If di by dt equal to 1 ampere per second, then equation becomes M equal to E. How to define mutual inductance? Mutual inductance for a pair of coils is numerically equal to induced EMF in the secondary coil when the current in the primary coil changes at unit rate. This is mutual inductance. Yes, what is mutual inductance? In general, we can define mutual inductance as mutual inductance between a pair of coil is EMF induced in a coil due to unit rate of change of current in the neighboring coil. Or simply you can write this definition, that is induced EMF in the secondary coil when the current in the primary coil changes at unit rate. This is mutual inductance. Now we can observe unit of mutual inductance. The unit of mutual inductance is Henry. Self-inductance SI unit and mutual inductance simply inductance SI unit is Henry. Now the mutual inductance for a pair of coil is given by the equation M equal to E divided by di by dt. Suppose if E equal to 1 volt, di by dt equal to 1 ampere per second, then M equal to 1 Henry. 1 Henry. How to define 1 Henry then? 1 Henry equal to 1 volt divided by 1 ampere per second. That is, mutual inductance for a pair of coil is said to be 1 Henry if 1 volt of EMF is induced in one coil when the current through other coil changes at the rate of 1 ampere per second. This gives 1 Henry. What is the definition of 1 Henry? Mutual inductance for a pair of coils is said to be 1 Henry if 1 volt of EMF is induced in one coil when current through the other coil changes at the rate of 1 ampere per second. So this is all about mutual induction as well as mutual inductance. So in the next class, we can derive an expression for mutual inductance of two long coaxial solenoids.